All right, these are the final 2 pages of the review here, and they were given an equation of the amount of water in a holding tank for a certain number of time. And so I went ahead and I put that into the calculator for Y1. I made a window that went from 0 to 10, and then I made my Ymin, Ymax be so I could see it. When I graphed it, this is what it looked like. All right, so you can see the volume going down, then coming up, then down, and then up, then down again. All right, so the first question says, at what time in the first 5 hours is the volume of the water in the tank at a minimum? So what I want to do now is I want to close this up a little bit. Let me go from 0 to 5 now. Okay, look, and here's what the water is doing up and down. It sure does look like the minimum is going to be right here. And so I want to get that point. So I could do that by going second trace minimum, and then go to the left of that spot, go to the right of that spot, hit enter. And it says my minimum was at time 1.657. So at t equal 1.657. And it says how much water was in the tank. That's the Y value. So that's 910.955. All right, so in those first 5 hours, that is the time where we were at our minimum, and that's the minimum that was happening there, okay? Now, we could, if we wanted to, graph the derivative and see when it crosses and get that relative min-max, but this was good enough to kind of just visually see it actually on the graph. During what interval is the amount of water in the tank increasing? So again, I'm assuming that we're only talking about the first 5 hours here. So initially, it sure does look like we're decreasing, then we increase up to this point, and then we decrease again. What I want to do, though, is I want to kind of make sure. So I'm going to go ahead and graph a second function that will be the derivative of this first one, all right, for x equal x. And for my window, I do need to make this have some negative values. So I'm going to go negative, say, 100 here. We'll see if that's enough or not. So if I hit graph, there's the volume equation again, going up and down for the first 5 hours. And you can see that I haven't made enough negative for the y. It will be okay for answering our question, which is when are we increasing, because we're going to be increasing when our derivative is positive. So I'm going to actually leave it for right now. And I want to see what this time is and what this time is. So I go second calculate 0, move up, make sure I'm on the red graph, and I'm going to go over. So be to the left of it, be to the right of it, hit enter. And it says the 0 is 1.657. That's what we had from before in part A. So this is another way of confirming that. So that'll be the start of this, 1.657. That'll be the beginning of the increase. And then I want to find the end point. So I'm going to go second calculate 0. And this one I can do a little faster. I can say that it's between 3 and 4. So I hit enter. And it gives me the 0 at 3.828. And if I had to justify this, I would say that the reason it's this is when it's increasing is because that's when w prime of t is greater than 0. W is the original function. This is when the derivative is positive. At what time in the first 5 hours is the rate at which the water is flowing in or out the fastest? Justify your conclusions. All right. So we want to know when are we at our maximum? Well, we can kind of see that the maximum would be right there. So if I go second calculate maximum, I'm going to go from net 2 to 4. And I want that maximum value in between there. And it gives me a maximum. Oh, I picked the wrong function. See, it's important to pick the right function. Let me try again. Maximum, slide up so that the red function's highlighted, 2 to 4, enter. And it'll go right on the top of the hill there. And it was at a time of 2.782. Okay. And if they want us to justify that, well, that's going to be a little trickier. What we'd actually have to do is take the second derivative on our calculator and set that equal to 0. so that we can see exactly where that switch happens from positive to negative. So that would be a little bit trickier to do. At least on the calculator, we can physically see where that rate was there. And D says, what does the mean value theorem guarantee on this interval? Well, because this is differentiable and continuous, the mean value theorem would guarantee that there's some point where the derivative would have to equal the average rate of change. Now, in order to get that on our calculator, probably the easiest way to do that is to go here and go alpha trace y1 and then go parentheses 3. This is going to give you the value at 3 minus alpha trace parentheses 1. So there's our y3 or w3 minus w1, and we get a value of that. And then we're going to divide by 3 minus 1 or divide by 2. And so our average rate of change on that interval is 203.245. Okay? So at some point on the interval 1 to 3, W prime t equals 203.245. That's what the mean value theorem guarantees. Because W is a continuous and differentiable function, and we may want to say WT is continuous and differentiable. If it wasn't, there would be no guarantee, there'd be no promises. But because it's continuous differentiable, somewhere in that interval, the derivative has to equal the average rate of change. Now we're given a couple of multiple choice questions here. For the first one, H is the product or the composition of this. So the derivative of H would be the derivative of the outer, leave the inside alone, times the derivative of the inside. So if we want to know what H prime of 1 is, H prime of 1 would be F prime of G of 1 times G prime 1. Now we go to the table. G of 1 is 2, and G prime of 1 is negative 3. So G of 1 is 2, and G prime of 1 was negative 3. And now I go back to the table, and what's F prime of 2? F prime of 2 is negative 2. So we get negative 2 times negative 3, which is a positive 6, which was A. So you have to do the chain rule there, and then have to kind of figure out that inner one first and then go back and find that secondary. That's not easy to do. That's what you do on that one. All right, and this one also is a form of that where h of x is sine of f of x. What's h prime? So you take the derivative of the outer function, derivative of sine is cosine, leave f of x alone, times the derivative of f of x, which is f prime. And so you look at your choices, and the one that does that is C. All right, then finally we were given a derivative graph, and A says, where does A have a local minimum between negative 3 and 7? So we'll have a local minimum when our derivative switches from negative to positive. This is the derivative, and this switches from negative to positive at negative 1. And then again at positive 6. All right, and again, our justification for that is that's where the derivative, that's where G prime switches from negative to positive. Whereas G increasing, G is going to increase when its derivative is positive. And this derivative is positive from negative 1 to 2. And from 6 to 7.